Let's further elaborate the concept of sliding mode control with the help of phase portraits. For that purpose, we consider the phase portrait of the pendulum system. You are already familiar with these phase portraits. And in addition to this phase portrait, we consider the phase portrait of two more systems. One system is described over here, x1 dot equal to x2 and x2 dot is equal to u. For this particular system, the phase portraits are described over here, and here is another system, x1 dot equal to x2 and x2 dot is equal to minus u. For this particular system, here are the phase portraits, and we use these phase portraits to explain the concept of sliding mode control. Here is the phase plane, x1 on the horizontal axis and x2 on the vertical axis, and this line depicts the sliding surface. And let's consider some particular initial condition. We see that this initial condition is not on the sliding surface, that is, here s is not equal to 0, therefore control action will come into play. And that is here, this u will be given over here. And since we know that this minus 4, this came from an upper bound on these terms, so this control action will somehow dominate all of these terms, and the overall system will be somewhat similar to these dynamics. That is, under this control, this system will behave somehow similar to this system, and that is corresponding to this initial condition. Trajectories will follow some path like this one that is depicted over here, and this initial condition, starting from this initial condition, trajectory will reach to the sliding surface. So as soon as the trajectories reach on the sliding surface, s becomes equal to 0, that is, there is this control action will become equal to 0, and now this term will be 0, and the system dynamics will be governed by these equations. This term will be 0, and for this particular system, the phase portraits are shown over here, and therefore trajectory will tend to follow some path similar to this one. And but as soon as these trajectories leave the sliding surface, s becomes non-zero. Control again comes into play, and now the dynamics of this system with this control action will be governed by some equations similar to this one, and therefore trajectories will follow a path similar to this one that is shown over here. This will follow this path and will again reach to the sliding surface, and again on the sliding surface control will be 0, and system will tend to follow a path similar to these phase portraits, and this action will continue until finally the trajectories reach at the equilibrium point at origin. However, one very important point which we need to emphasize is that this procedure, which is explained over here, is explained in discrete steps, but actually this process will not happen in discrete step. This will be a continuous process. That is, this control law will bring the trajectories to the sliding surface, and then as soon as the trajectories leave the sliding surface, the control action will again come into play and will keep the trajectories on the sliding surface, and therefore the trajectories will slide on the sliding surface to finally reach at the origin. So you see that this word as soon as means this control law will be in the form of impulses, some constant values with duration tending to 0. So this control action will be in the form of impulses, and this ideally trajectories will not leave the sliding surface, because as soon as the trajectories tend to leave the sliding surface, the control action will come into play and will keep the trajectories on the sliding surface. In the next lecture, we shall show some simulation results for the design of sliding mode control for this pendulum system.